Okay, fine. So the other recording, I don't know, it was trying to fix itself. Fine. So I also have my board now. Let me see. Am I sharing anything? Okay, share the screen. Okay, fine, good. So now we are ready to continue. Fine, so very quickly, let me pick it up from the data we used last time. We were trying to predict the office prices of a Nairobi office, the monthly rent that someone might need to pay. And we said last time, in any regression model, we have two important variables. Okay, the independent variable, which is X, and the dependent variable, which is Y. And they come in form of vectors. So all these values here, X values will be collapsed into a vector and Y values into a vector. So this is called a one-dimension problem, where we just had the only X that we had last time was the size. So we say that the price or the monthly rent depends on the size. So last time we just had the size of the office in square feet or foot. It was determining the Y. So the Y is price. So if I may, I don't know if my pen is back. Price. So this is what we were simulating last time. Then we came up with a line of best fit that was trying to now be able to predict the price. And this is the model that you are also editing in the coding assignment. You are regulating this model. Good. So as we start feature selection, I just want to start by rechecking the regularization that we had checked on. And remember last time we had already rechanged the equation from, so the equation of a line is always y is equal to mx plus c. Okay, so this is, so we transformed this, okay, to this. This is what we did last time. You can check out the video and the notes. So instead of m, now we have a variable called w. Okay, so it's just a notation. And now this w stands for a weight. And then instead of c, we have a b. So the b stands for a bias. And why do we transform this equation to this? You will see, because even the deep learning theory is now going to be built from this. So W now becomes the new slope, and we have another variable called bias. So having transformed from this to this, okay, so remember that we were learning the line of best fit. How do you learn the line of best fit? Just by trying to learn the best M and the best C. That's what gradient descent was doing. Okay, so now we just retranslate that one. We are trying to learn the best W, the best weight, okay, and a bias that can define the line of best fit. And that is how a one-dimensional problem was looking like. So actually, when you come back here, you see that the regulation or the regularization is based on the weights, okay? The weights which have now taken the place of the slope, okay? So you see the regularization is based on the weights. Okay, fine. So the question is, how does L1 actually punish the large weights? How does it actually do it? So the key thing here is that you see, we say that lambda is a hyperparameter, and the hyperparameter is actually what do you say? It's actually going to be set later. From Friday, we will learn about hyperparameters. So now we want to ask ourselves, how actually does this L1 actually punish large weights? Good. So the idea here is that if you look at this properly, this part, okay, which is in red, which is called the regularization term, or actually the penalty, you start to begin to see how L1 is going to punish, and that is going to be important. So lambda must be a value greater than, okay, it has to be greater than 0 in this particular scenario. So we say that we transform the loss function. We know that learning takes place by trying to find the minima of the loss function. Okay, that's how we optimize. So, and how do you find the minima? By finding the derivative. So we know the derivative of this part from our regression, okay, that we did first is actually this part. Okay, that's the derivative with respect to m, like we did last time, but now w has taken the place of m. So we say the partial derivative with respect to w is actually, so this part is like this. So the question is, what is the derivative of absolute w? Okay, this was part of the assignment, and the derivative is actually that. It's absolute w over w, okay? So now the question is, what happens when the weight is positive? Okay, you know, when you say that it punishes, it means that if it's positive, it must tend to reduce it. If it's negative, it must tend to increase it. So in short, what L1 is going to do is going to pull weights towards 0, okay? It's struggling to make weights to be 0. So let's look at a scenario where W is a positive number. So if W, for example, if the weight, okay, or the gradient, okay, if you have one, just one X. So let's say if the weight is positive, okay, and you see how the derivative is looking like, okay. So when I have, let's say when I have a number like 2, let's say a weight is 2. Okay, a given weight is 2. How will this part look like? So the equation there will be absolute 2, okay, absolute 2 over 2. Okay, so absolute 2 over 2 is just a positive number, okay? So absolute 2 over 2 is actually 1 because it will be 2 divided by 2. So on the other side, let's look at W being negative. When I have a negative weight, how does that part look like? When I have a negative weight, so just trying to understand how L1 actually punishes the weight. So if the weight is negative, say negative 2, okay, according to this part of the equation, it will be absolute negative 2 divided by negative 2, okay? So it will actually be negative 1 because absolute forgets the direction. So it would be 2 divided by -2, which is actually -1. So if you pick any number on the positive side, it will always be 1. If you pick any number on the negative side, it will always be -1, okay? So that's why you find some derivatives are written like plus or minus, depending on what the weight will be. So that part could be plus or minus, whatever we have, all of this. But I don't do that because the negative does the magic. So this is actually the lasso that I ran on my NLP models that I actually just brought it here. So now here is the case. If W is positive, then this part will be positive. Okay, if I only have one W, so we forget the summation, we are not adding anything, we only have one W. So if the W is positive, so this part actually is positive. But you see, lambda being greater than 0, so it will be negative and a positive, which actually turns out to be a negative. So this weight which is positive will actually be negated right here using this sign. If my weight is a negative, so I'll have a negative with a negative here. So a negative and a negative now becomes positive. It means that that weight will actually be pulled towards the positive side. So the idea here is just simple. The number line, no, that's not a proper number line. The number line, different pen. We all know the number line, even if I don't draw it well. The origin, 0 is here, the negative side, and the positive side. So if actually L1 is working well, if the weights are positive, L1 tries to draw them towards 0 by subtraction. If they're negative, it tries to draw them towards 0 by addition. Okay, that's why I put up the negative sign here. So actually now we understand how L1 works, and this is called regularization. Okay, so what is regularization? Trying to reduce the weights of irrelevant features, and that's what we want to do today. So L1, number one, it can be used to do regularization. Number two, it can be used in feature selection that we are going to see today. So fine, yes, Gladys. Your hand is up. Yes, yes.
Oh, it's in the afternoon. I wanted to ask about the partial derivative of W.
Yes, absolute W.
Yes, and
Yes.
I thought it's supposed to be W over the absolute value of W.
The other way around.
Yeah.
Okay. Any other concern before I answer that?
No, that's just the only concern right now.
Okay, fine. So the derivative of absolute W, we said that this is the problem with, you remember even the mean absolute error, it has this absolute thing. So calculating the derivative of absolute, sometimes they can be quite difficult. Now, Tyrone, you had the same question? I thought your hand was up. Yes, yes.
I had the same issue.
The same issue. Okay, fine. So, so if you have delta x, now this is mathematics. You guys, you found the derivative to be what? It should be delta x over x. Okay. But I wouldn't be afraid at the same time, because if I take the inverse of this, you see the way this function behaves is that it will always output 1 and -1, respect for all real numbers, because you're dividing a number with itself or a number with its absolute. And yes, even if you see the behaviors here, even if you interchange, it will still be the same. But I think the derivative of how I did it by hand is that I think it should be like this. Maybe I have to revisit my calculations a bit. But how actually do you compute the derivative of this one? You can use linear programming kind of knowledge, so computing this one is not that direct according to what we revised. So it depends with the source that you checked out. Personally, I normally find this one as the derivative anyway. So even if we interchanged, still the same. Okay, so either way, we can work with this one, mine, can interchange maybe. So fine, so that's how this thing kind of behaves. It kind of pulls things towards 0. So if you ever forget, just remember this part and actually the signs, the positive and the negative, etc. So if you looked at other lassos, you could find they give 2 equations for this, one for the positive, the other one for the negative. Me, I summarize everything using the negative sign that we have here. Good, so now today we want to look at feature selection very quickly. Fine, so we want just to upgrade our regression formula. From y is equal to mx plus c, we have moved to y is equal to wx plus b. Now we have a general formula. Y is equal to w1x1 all the way to wn xn plus b. Okay, so this is whereby you have multiple features, okay, or you have multiple what guys in databases could call columns, okay, or you have multiple variables. So when we began, we say that there are 2 variables, the independent and the dependent. Okay, so independent is causing the change in the dependent. So for example, in our example, we say that the office price depends on the size of the office. Okay, the monthly rent you pay depends on the size. So the size is the independent and the office price is the dependent. Okay, so you always have one dependent variable, always, but you can have multiple independent variables, okay? For example, we say that apart from the size, the office price might depend on many other things, location and availability of electricity, reliability, and so on, so many other features, okay? But it is still office price that we're interested in, or the monthly rent of an office. So this is called the general linear regression formula, okay, where you have multiple independent variables. So when you have only one independent variable, we actually used linear regression. When you want to improve the capacity, we used polynomial regression, where you give some powers here, squared, cubed, whatever. That was the polynomial regression. When you want to regularize, you use L1, which is lasso regression, or L2, which is ridge regression. Those are your types of regression. But now when you have multiple independent variables, okay, you use stepwise regression, which we are not going to actually run, because neural networks can do regression much better, okay? So the thing that we focus here on today is number 1, having multiple independent variables. That's the first thing. And then every independent variable has its own weight or its own gradient, or whatever you want to interpret. So let's just call them weights. That is the standard. So that's what you're seeing here. So weight 1 is for x1, weight 2 is for x2, up to weight n, which is for xn. So this is the general linear regression. If I want to find the line of best fit here, that line of best fit can be discovered using stepwise regression, okay? Which we are not going to code from first principles that like we did linear regression. So now, what are the issues when I introduce multiple independent variables? What are some of the issues? So more features or more independent variables. So right now we switch from calling them independent variables, which is a statistical term, to features, which is a machine learning term, okay? So features is the machine learning term, calling them columns is the database term. So features are better. So more features does not always mean a better training set. Some of the features are useless, okay? That's why we want to do feature selection. Which features are the most important? When I want to determine or to predict the office price, what is the most important feature? Is it the location? Is it the furniture in the office? Is it, so it depends, okay? So what is the most important feature, and how can we calculate, how can we find the most important feature? Because you'll have a data set with even 100 features. You won't use all those features for training. You will do feature selection, then you will end up with maybe 20 features out of 100. Okay, so that's what we are going to do today. And we are going to do that using L1. Okay, so if you are already thinking ahead, is that those features whose weights will be set to 0 with L1 are the features we are going to drop. Okay, so that's how important L1 is. It is pushing the weights towards 0. All the weights that are 0 will be dropped. Okay, the rest will remain. So not all features or all variables are important. Some features or some variables have missing values. Others have little information. Others suffer from a problem we call multicollinearity problem. Okay, so multicollinearity means that some two features are deeply interrelated, okay, such that there is a whole problem. You see, the key thing here, let me summarize it for you so that you don't struggle, is that when I have too many variables, okay, or too many features like this, x1, x2, up to xn, the way this line of best fit is identified is that first we will study y in relation to x, okay, x1, holding all other factors constant. It's just like the way we do partial derivative, okay? When I am doing partial derivative with respect to x1, I switch off every other x, I forget them. But now the problem is that if I have multicollinearity, let's say x1 and x2 are related, if I switch, if I say, let me study y hat with relation to x1, there is a problem because x2 is related to x1. Okay, so my model will not be that accurate in the long run. So that problem is called multicollinearity. We say that x1 and x2 are collinear variables, okay? So the key thing that we want here is that we just want x1 to be independent, x2 on its own, xn on its own, and then we want to measure how is x1 causing the change in y hat, or we just assume the rest as we study one particular variable. That's why it's called stepwise. Step 1, switch every other x, focus on x1. Step 2, that's how it kind of finds its line of best fit. We won't do that. So since some features are useless, others are suffering from some problems, and others have missing values, and so on and so forth, we desire to avoid all these. Most importantly, multicollinearity is a very big problem in regression. So the question is, which subsets of features are more significant? Which features are the most important? That's the question that is now being asked, and that is going to be answered by Mr. Feature Selection. So it's very simple. I have actually summarized here. So feature selection, FS, is the answer to that question. So what is feature selection? It is just a way to identify the subset of variables that are important. What is important? These are the variables that contribute the most to the target variable. Okay, so if I'm looking for an office, what are the most important things that I want to consider? For me, I would think location to be one of the most important things, or maybe something else. Now, that depends on the person sometimes. Okay, and that is another area of AI that I don't want to go to yet now. It's kind of a personalized data set. The features that I consider may be important, may not be what someone else considers important, and we are going to see how to deal with that. So right now we are just saying there is a global rule that says that when people are looking for an office, okay, these are the most important things they look at. So it is a search problem. We want to search through all features and then come up with a smaller set of features which are actually the most important. So there are three ways we can go about this. There's what we call the embedding method, there's what we call the filters, and finally what we call the wrappers. Okay, we will focus on the embedders and do it. The rest are actually easy. We will have a small assignment on the wrappers. So why do I want to do feature selection? Number one, it helps me to avoid the problem at hand, overfitting, because I will have lesser irrelevant features. Okay, so the more you have relevant features, the more you generalize well. Okay, that's the key thing. So feature selection is another way of reducing overfitting. So guys, how do you avoid overfitting? Number one, the most important, regularization. Okay, that's number one. And you know that regularization just punishes the weights. Okay, like we have just seen what L1 does. You can also study L2. You will see how it punishes the weights also. Now, so regularization is the major way of avoiding overfitting. Then number two, I can avoid overfitting, remember, by increasing capacity, model capacity. You remember that, model capacity. And now we have a third way, okay, perform feature selection. So number one should always be regularization. That's the main thing, because you see we are also deriving feature selection from a regularization technique, which is L1. Fine, so why is the feature selection important? Number two, the model will be more accurate if you do feature selection. That means before we do training, we actually do feature selection. So feature selection is normally done before training, okay? Then number three, it's going to speed up the training, okay? How? Because I have now lesser data, okay? That's feature selection. After I select, let's say I had 10 features, and after feature selection, I only have 3, then I have a smaller data set. So the model will train faster. So those ones are not too cram, but to understand feature selection. So let's see feature selection using embedded technique. Now, embedded here means like what we are just doing to the loss function. We are just embedding a penalty. Whether that part is usually called the penalty by statistics, guys in statistics. You see, we're just adding. So we took the normal loss function and then we added something in there. So now, that's why it's called an embedded technique. So I go all the way down to where I was quickly. So feature selection using embedders or embedding. So they make their decisions on feature importance in every iteration. Remember, the loss function and its minimization is usually done in every iteration. If you track the iterations like we did last time, you will see. So we say this is an iterative method, okay? And the the chief embedders are usually the things we are using in regularization. So here we will use L1 as a, that's why I put it as number one. So how can L1 help us to do feature selection? So L1 falls under embedding technique for feature selection. That's the key thing. Okay, so these features are removed and the remaining form a subset that is then used in training. So when does feature selection take part? Before training. Okay, that process of before training is usually called data pre-processing. Okay, so pre-processing is the activity that takes place before training. So anytime you're given data out there or when you want to build a model, in fact, the first thing that actually takes place is what we call data cleaning. That actually takes a lot of time to clean the data. Then after cleaning, you can do pre-processing, where you can actually set your hyperparameters like we are going to see on Friday. And you can do things like feature selection. Then after that, you can be able to train the model. So today I'm going to take you through the first class of preparing a data set, okay? And then we will be able to do feature selection. That's the thing we're doing today together. So we have got few slides here. Number 2 is the filter methods. Now in filter methods, is where you can use some metrics. You remember information gain that we were using in decision trees. It was just a way to do feature selection, which is the most important feature when I want to identify if a car is fast or not, if you remember that example. Is it the weight of the body? Is it the presence of a turbo or not? So what is the most important feature? So we did information gain. Other things you can measure are the chi-square. You can use Pearson correlation. You can use PMI. You can use Gini or Gini index. So in filters, you compute some things and then you make your decision based on the numbers. Okay, so that's the filtering technique. We will also see examples of this. These are some of the things that can be measured from a confusion matrix and can be used for filtering. Like, how do I get chi-square from a confusion matrix? It's actually this long formula. So you don't have to cram all these formulas. We're just going to apply them. Finally, the wrappage, and this is the third and the most final way of doing feature selection. And here, you're just going to have three important ways: forward selection, backward elimination, and RFE. You can try to check them out. What these guys do is that they start with, let's say, an empty set of features. They go through iterations, then they will end up with a subset, okay? Or they do the other way around. They start with all the features, and in every iteration, they keep on eliminating, okay? And then finally, they have empty set if you don't stop them. So you have to decide where to stop, in what iteration, and how many features do I want. So maybe out of 10, choose the 3 important features. So in these models, you can actually choose the 3 important features, okay, or something like that. So in forward selection, it starts with an empty set of features. Then in every iteration, they keep on adding features, okay? The best feature is added in every iteration. And then if you don't stop it, S will keep on growing until it has all the original features. It started empty, it will have all the features. But now you have to tell it where to stop, okay? So where does it stop? You are going to tell it the threshold, and we are going to see that. Same happens to backward generator. It starts with all the features, and if you don't stop it, it will kind of end up with an empty set, okay? But before it ends up with the empty set, the last one will be the most informative feature in the data. Okay, so this technique, you can actually use it when you want to know out of all these 100 features, which one is the most important? If you want to know it, run a backward generator. It will start with all the features, it will do the elimination, and then it will end up with an empty set. Then you backtrack one step. When you backtrack one step, it will actually give you the most informative feature. Okay, good. So which one do I use? I am confused. There's this feature selection story. There's the embedding technique, the filters, and the wrappers. So which one do I use? Now, we are going to get to a point in machine learning whereby we don't have the answers. So it just depends on what you want to do. What do you want to do? Do you want to get the most important feature? Run a backward generator. Do you want an efficient method? Okay, or do you want an accurate method? Okay, so some are efficient, others are accurate. Remember, you will always struggle with accuracy versus efficiency in machine learning. So let's have a look here. Embedders are more accurate, but inefficient. Okay, so what's the machine learning advice? It is suitable when I train a data that has less than 20 features. Okay, so who says less than 20 is just a best practice? You can say less than 30, it depends with which data you have. This is just like the general advice. So the lesser the features I have, then I can use embedders. Okay, and I want accuracy. Now, filters, where you do things like information gain and the Gini index, etc., they are less accurate. Okay, they are less accurate. But if I want to detect multicollinearity in the data set, then this is the way to do, one of the ways to do. From the other week, we will see things like PCA that can also be used to detect multicollinearity in a data set. But if I want to do multicollinearity tests in an efficient way, I can do filters. Then wrappers are more accurate but inefficient. You can run a backward generator to get the most important feature, and so on and so forth. So just for summary, we will illustrate today using embedders. It is very easy. We are not going to code from scratch. Today we encounter our first library that we are going to use. So anyone with any question on that small feature selection issue? You can go through all this, and just you must know how L1 punishes the weights, and just a way to be able to explain that one. Good. So to be able to see how we can use L1 to do feature selection, we have machine learning class task 2, which you can actually check out from the e-learning. Just run there. We'll write a few lines of code. I can give a 5-minute break, then we will be back. So you can use the 5 minutes to stroll around, get some water, like I'm going to do. Then I restructured this a bit, so you'll be finding the lecture videos down here, and the notebooks down here, and the data, and the tasks will always be down here. So today's task is this one, machine learning task 2, and then I have upgraded or extended the data. So you will download this one, you unzip it, then we can meet after 5 minutes. Okay, so we can now check out the data set. So you can open the data set, use this one. Good. So I just came up with about 15 columns, but we will extend it. So this is for the purposes of understanding. So I maintained the size and the price column, but I added some more independent variables, more features. So these are the features we have here. And the task is following. So you should have okay, so this is the task. We want to do feature selection. Out of these features, 1, 2, 3, 4, 5, 6, 7, 8, 9. We want to see which features are the most important that will actually be used in training. So, and we are going to use the embedded technique using L1. Good. So step one is actually to prepare the data set. Actually, so how do we prepare the data set? Number one, we have to do data description. So assuming I was looking for an office, and these are the things I'm interested in, then I went to the field, just drove around asking prices. I went to Karen, Madaraka, Buruburu, Donholm, Langata, and yes, I think I went to those places and I asked general questions on these ones. I measured the size and then I was given the price. Then I want to use that as my training data set to train my linear regression model. Then I can now predict if an office is in Karen and has this and that, what is the most likely price? So that's what linear regression does. So we start by, so after going to the field, collecting the data. So any data that is well collected, you will find that it has a description. So anytime you land on a data set, try to find its description. So today, part of the exercise is just to come up with a small description, which we can actually just prepare on a text file or on a Word document. So what are some of the things you want on your description? So the first thing I should explain is like me being the data collector, I have to explain all these columns, okay, what actually was collecting. So I was interested in number one, the location. So please prepare your document. We'll be preparing this together. So you have to kind of explain all these that you have here, or it's just a reverse engineering thing, because actually, number one, I had the location, I had the, so what that means is whether the office is furnished or not. That's the second one. And after having that, you can always code name it. So me, I code named it like that. I code named the location to be LOC. Okay, so you can prepare this in the best way you think. We can use tables. The next thing I was interested in is the ambience, the environment around. So I codenamed this AMB. The next thing I was interested in, how close is the office to a school? So proximity to school. I don't want one that is very close to a school because of the noise. Proximity to school, so I called this progs. Okay, like that, I could name it that. Proximity to road. Is there a road closer? Prox road. Proximity to a mall. I might want it to be near a mall because I might need to buy some stuff, proximity to a mall, or even maybe attract some customers depending with what my office does. The next one was availability of water. Do I have to buy water, or is there piped water? Okay, just code named that water. Then are they offering housekeeping services like cleaning, or do I have to arrive in the morning and start cleaning? And I just code name that HKSAR. So if you download a dataset, this is what you will get. You have to look at the description to know what am I looking at. Finally, the size. Okay. Size of office. I just called that one size. Good. So those are my variables or features, and that is their description. So when you're preparing the description, the next thing you want to prepare is the possible values. So actually doing this in a table will be good. What are the possible values for location? Is actually everywhere that I went. So we have the Karen, Madaraka, Buruburu, Donholm. What are the possible values for furniture? Is yes, meaning it is furnished, and no, meaning it is not furnished. Ambience has 3 values. It can be serene, meaning it's very cool. It can be noisy, or it can be semi-serene. Okay, proximity to a school, all these are yes, no, yes, no, yes, no. And then the size is actually the size in square feet. Good. Then after doing this, the next thing that happens after this is very important. So I want you to pay attention. And I actually want you to do this. So the next thing is the type of data that I'm looking at. Okay, I will start with the first one, this size that we had last time. If you remember the scales, the 4 scales that I gave you when we were revising statistics, okay? So anyone who can remind us the 4 scales of data that we talked about during statistics revision? What were their names?
I think it was nominal, ordinal, interval, and ratio.
Yeah, very good, Vanessa. Very, very good. Yes, nominal, then ordinal, then interval, then ratio scales. Okay, those are the 4 scales. Now, today we are going to use that information. That's why I revised them. So if you don't know what you're talking about, you might want to go back to statistical revision. And let me see. Statistics and probability revision. The 4 scales of data. Yes, so these are the 4 scales of data that we have. So no, they're these ones. Yes, and they have these properties. So you can revise these ones. You will always be using these ones. So automatically, the size is a ratio type of a scale. Okay, so just write there a ratio. A table could have been better, so you can be making tables when describing your data. Sometimes you don't have to do this because you're using someone else's data, okay, that they already collected, so you have to look at it. So the size is a ratio type of scale. There we don't have a problem. I'll say what a problem is. What do you think location is? Which type of data do I have there? Karen, Madaraka, Karen, Buruburu, Donholm, Langata. Of course, it's not numbers, they are words. So which type of scale is that? Yes, Isaac.
Could you say it's a nominal scale?
Yeah, good. It's a nominal scale. So we just write here nominal. What's a nominal scale? It just has identity, okay? It does not have magnitude. We cannot be able to have a numerical difference, okay? We can say the difference between, let's say, Langata and Donholm is 10, unless you're looking at the distance between the estates or something. Okay, so we call that a nominal data set. Now we have to determine the rest. Please determine the rest, then you call me and give me the list so that we fill all this. Furnished. So what do we call furnished? Is it nominal or ordinal? Because interval and ratio, they have to be numbers. Someone? Furnished? Furnished is a yes/no question. What do we call yes and no's? Okay, we have some answers from the chat room. Guys are saying ordinal. Not really. Actually, furnished is just nominal. Okay, but it depends with how we look at it, because maybe furnished is better and not furnished is not better. In this case, I just took furnished to be nominal. So today, let's just work with nominal here. For ambience, so we'll just say what is nominal, all the nominals. Nominal, okay. So the next thing that I took to be nominal is the following. So that always depends again with the task. And what I took to be ordinal are the following. For example, if a place is noisy, I consider it to be bad compared to serene, okay? If a place is closer to a school, I consider it to be bad. Closer to a road, I consider it to be fair. And closer to a mall, I consider it to be good. Okay, so depends with how I look at it. That's why I was telling you about a specific kind of looking at a data set. But for now, let's work with these scales. Okay, so why am I pointing out these scales? Because we want to prepare the data set. Now, machine learning models mostly will not work with a column like this one. See this one where you have nominal data? I won't work with that. In fact, if I feed that to L1 now, what you will see is an error. So the question is, how do we deal with this data set? How do we prepare our data set? Is the following. So there are usually ways that you can use to transform your data, okay? So I want you to note down the following. One of the major ways to transform nominal data is by using what we call one-hot encoding. Okay. And the other way, so for nominal data today, we will use one-hot encoding. I will describe what that is. For ordinal data, we are going to use integer encoding. So the key idea here is that we want to train our model, but we don't want our model to consider the difference between Karen and Madaraka to be a numerical value, okay? We want it to know just that Karen and Madaraka and Buruburu and Donholm and Langata, they're all the same, but Serene and Noisy, they're not the same, okay? There's an order here. We want Serene to be good, semi-Serene to be fair, and Noisy to be bad. Okay, so this is called ordinal data. There's some order here, but here there is no order. You can't say Karen, Madaraka, then Buruburu, then Donholm. No, there is no order. Okay, so for nominal data, something called one-hot encoding. That's what we are going to use. And for this ordinal data, you're going just to use numerical. So for example, we say that Serene is equal to 3. Then we say that semi-Serene, this is just an example, we are going to run that in a moment, is equal to 2. Then now Noisy is equal to 1, okay? You can use that scale so that if I consider the difference between Noisy and Serene, it's a 2. Okay, the difference between semi-Serene and Serene is actually a 1. So it means that semi-Serene is closer to Serene than Noisy is closer to Serene. Okay, so Noisy is 2 points away from Serene. So we have maintained our ordinal logic. Okay, in ordinal data when we use integer encoding. So this is an example of integer encoding. Why is proximity used as ordinal? I take proximity to be ordinal because of what I am considering. For example, proximity to a school, and no means that the office is not close to a school, okay? So I am assuming that if an office is close to a school, then that kind of means that there will be noise, especially if it's a primary school. Children will be playing. When they are going home in the evening, they'll be shouting on the road. Okay, so it is totally subjective. So in my case, because I was the one looking for the office, I want to consider this as an ordinal data. So no is better than yes. Okay, so if an office is closer to a school, I want that to be different from an office is not closer to a school. And I want there to be some logical difference in terms of magnitude. So for nominal data, you don't want to have that kind of thing. I can't say Karen is equal to 1. Then I say Buruburu is equal to 2, Langata is equal to 3. No. Automatically, if I feed this to my training model, it will take the sense as numbers for what exactly they are. So it might even start to generalize the model in terms of the numbers. Okay, so actually this problem is solved using some encoding which is kind of neutral. So here we are going to use one-hot encoding, and this is how one-hot encoding will look like. It will just list all the estates, okay? They are about, so I counted 1, 2, 3, 4, 5. There are 5 estates. So maybe it can code Karen like this. 1, 2, 3, 4, 1, like that. Then Buruburu could be, so let me just give an example with the opposite. So let's say it can code this like that. Okay, so a 0 there, then it codes the second one like this. 1, 2, 3, 4, 5. Okay. Then it codes the next one. So this is called one hot encoding. 0, 0, 1, 0, 0. Okay. Then it codes the next one. Madaraka, so Langata. It codes it maybe 0, 0, 0, 1, 0, and so on. So the idea here is that if I have Karen in any column, this will be its value. So these are not numbers. This is just an encoding. So you don't want to feed this into a column that understands them as numbers. And we are going to see how to deal with this one. So one hot encoding always looks like this. It has a relationship with binary encoding, okay? And we will mention it as we go by. So this is just introduction to how to prepare the data set. So you have to transform all the nominal, okay, and the ordinal features. The ratio and the interval, they remain because they are numbers. Now, both nominal and ordinal, they are known as categorical data, okay? So in short, we just say you have to transform categorical data. So transform categorical data, okay? So I could ask you to transform categorical data. You can just use one hot for nominal and integer encoding for ordinal because you just want to preserve the order. Good. Any question there? I saw something on the chat. There is my chat room. Yeah, there's a very good question here. And I was actually about to mention it. Someone is asking, does it mean that there is a collinearity between, let's say, proximity to school, okay, and the ambience? That's very true. That's perfect. I really like the thinking here, because that's what I was actually just to mention, that you see ambience, okay, ambience actually is the serenity of an environment. So if there is a school, okay, maybe there is noise if there is a school. So there is actually a relationship between this column and actually that column, okay? And anytime there is a collinearity, some columns will be dropped, then the main column will be maintained, because if I only have the ambience information, then having proximity to school, proximity to road may be redundant. Okay, that's the intuition in the model. Okay, that's a perfect reasoning for feature selection. And that's where multicollinearity comes in. Okay, so very, very good. Very good, Kevin. Fine. So guys, let's just quickly do this. You can do it halfway, then you can finish. It's a class task. There might not be an assignment on this, maybe until Friday. I will see. So how do we do this? Again, I prepared something small. So not this. So you can open the, I think there's something on the task. I don't know how I call it. Yeah, it's still on the task 2. Good. So we want to do this. We want to encounter our first machine learning library. That one is called skitlearn, okay, or sklearn or scikit-learn. I like calling it skitlearn. So it's just a scientific kit for doing machine learning. So it's a machine learning library. Okay, so skitlearn is machine learning library. Some other libraries are deep learning libraries, okay, like TensorFlow. Now, TensorFlow is built on top of Keras. Keras is a deep learning library, but it can be challenging to use. So TensorFlow works on top of Keras. We will use it when we get to deep learning. So today, why do we need a library? It means that today we are not going to code like regression line by line, but we're actually just going to call a method or to do some imports, and then it will do the regression for us, etc. But we just want to demonstrate how to prepare data. And anytime we are talking of data, pandas is the library where you manipulate data. So I've just added a few links that I think they're important. Okay, so you can go ahead and just open them quickly. We code this thing. So this is an example of one hot encoding using pandas. Okay, it's actually very simple. And then, yes, so I will just open all this. And more, so you can check out documentation. So the more you code, the more you learn. So nothing to be intimidated of today. So fine, so guys, let's go to Colab. We make this notebook. So Colab, I had coded it a bit before, so I'll just take you through how I just coded it so that you understand. Then again, the principle in the fewest lines possible. So I'll just make a new notebook. You can do the same. You can use the dark option for you. Mine, I have to put on some light. Okay, fine. So we can start because we are using pandas. Why not? So import pandas as PD. Can zoom a bit. And then, yes, so import pandas as PD. We are also going to use matplotlib. So import matplotlib. Okay. Also in the example, I used matplotlib.pyplot. Okay. Then, because we are not going to write our regression, okay, so we are actually just going to say from sklearn, this is how skitlearn is used, okay. And the idea here is that to use the sections of the library that are used for pre-processing. So you see, I just added this link here. So you can just say from sklearn.preprocessing, okay, unless you want to do what they're doing here. So we can just say from sklearn.preprocessing, okay. Then actually, what do we want to get? So just want to import the encoder. So here we use something called label encoder. I'll explain that, what that is. Then also from sklearn, it's the same library. It's a machine learning library. It can do pre-processing, it can do regression, it can do neural networks, it can do a lot of many stuff. So we can just say still from sklearn.linear model. So this is where you get your linear stuff. You can check out the code that I'm just using here. I've opened it here. So you have all your linear regressions or regressors here, okay? And you can see it's just the same thing that we are doing here. So you can do things like these ones. So from sklearn, import linear models, sklearn.linear model. So I am inside there. And then we want to import something called the lasso. Okay, so you already know what lasso is. They call it lasso CV. Okay, fine. So you can check out the lasso for sklearn. It's the implementation of lasso in scikit-learn. You can actually see the optimization function and the parameters it takes and the attributes. Now here, as we are using delta, okay, we are using delta. Guys in regression, they call it alpha. The reason why I didn't use alpha here, where are those notes? The reason why we didn't use alpha is because we had already used alpha to signify the training rate, okay? Here, the learning rate, I mean, here. So we use lambda. So anytime you see alpha, just know they're talking about lambda. So you see from sklearn.linear model import lasso CV, okay? And these are some of the things we can be able to do. So anyway, quickly, I think we will need these and more according to the code that I made earlier. So now the next thing is, of course, to, let me see. Label encoder. Okay, fine. So I'll cross the bridge when I get there. Want to open the data set. So you already know how to open the data set. We can write the lines. You can check out from previous what we did from google.colab. Okay, import files. Okay, then uploads goes to files dot upload. So now you can grab your CSV here. Where is that? Machine is really hanging. Yeah. So you can grab the guy and place the guy there. Then I saw something on my chat room. I don't know where it is. Okay, fine. So we have the data. You can now even go ahead of me, by the way. Don't have to wait. There's not always one way to code. So the idea here is that now we have the data. You can just say the data. You can even rename the data if you want to. We read this using pandas. Pandas. Read CSV. Okay. And actually the name comes here. The name is too long. Nairobi office price ex.csv. Okay, fine. We can just try to see if our data is there. Data.head. Good. Someone's mic is on. Let me see. Okay, fine. So, okay, fine. So the data is here. So we location, blah, 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 like so. Good. Then the next thing that I just did is the following. I just manually identify the nominal and also the ordinal. So I just said here nominal is equal to, I made a small list, and I also did ordinal is equal to, because we want to, remember for the nominal, we want to do one hot, and for the ordinal, we want to do integer encoding, okay? So you can place all your ordinal columns here and your nominal columns here. So for example, we considered location to be nominal. So I'll just place location here. The next thing we consider to be nominal is furniture. Furniture, so you can type faster than me. The next thing was water, yes, availability of water, but the column is called water. HK, services, size is okay. Then for the ordinal, we just said we use ambience, AMB, and then we use all the proximities. Okay, so you just want to place all of them here. Proximity to a road, and finally proximity to the mall. Good. I think those are the ones. Fine. So the idea now is to for the ordinal, we want to do integer encoding, and for the nominal, you actually want to do one hot encoding. One hot is very easy, but now doing nominal is doing ordinal is where you might need a few lines. So again, I just found the easy way is to look through and to get every value in the column. There are other ways you can do that, but looping through seemed to be easy for me. So you can just say for, okay, fine. For feature in ordinal, okay. Then I just want to say data. You see, when I say data and I call the particular column, we'll actually see the entire, like an array. So I'll just say here feature, so that when I'm dealing with ambience, I will have the entire this thing for ambience, okay? And the idea here is just to place that inside, let's say, a value. Okay, so you can just place it inside a value. Good, and you can just try to print the values. It will be chaotic, but you can start seeing. Okay, so you actually see for ambience, for school, and so on. You actually have the access to the values. Then it is these values that you want to transform, okay, into some numbers, okay, the encoder. And then from there now, we will rewrite. So how do we rewrite the column? Again, it's very simple. That's why I put up this one here, how to rename, how to rewrite, how to add columns, and it's very easy, but it's good always you know how to deal with data frames. It will always be helping you. So what's a data frame? It's actually what has been formed here by pandas. So we call them pandas data frame. So after doing all the things, we'll just say data feature, and then this is going to be equal to the transformed feature, okay? So we can just say transformed feature or transformed F. Good, so the question is actually how do we transform that feature? So now I have to come back to this import. Why was my import not working? Let me see. Label encoder. Maybe it's lunchtime. Label is spelled wrongly. So it is
Label.
Label.
Yes.
Okay. I'm really feeling hungry, so just hang on. We'll be done in a minute or two. Okay, thank you very much. So now, what do we do here now? We have the encoder. We can just say encoder. You see, encoder is a function, so is equal to label is EL, label encoder, like that. So we have our encoder after importing it from up there. Then we want to say, so this is what the documentation told me, encoder dot fit. There's a function called fit transform. And then that's where we are going to pass our value, okay? This value here. It will transform the value for us into a label, kind of. Anyway, let's have a look at it. So this is what I want it to be. So let me see. And so before we mess up the data, we just want to print and see how it looks like. Okay, fine. So what is not defined? Okay. The time is really challenging. Okay, fine. So these are some of the transformations that we have for the ambience column. So you see the value serene has been given 2, followed by semi-serene a 1, and then noisy has been given a 0. So you see the order has been kind of maintained. So the best way to see this is to say, actually, so I will just undo so that I really have that one. So I just say equal to that one. I will do all the transforms. Then when I'm done, I want to see my data, how it looks like. Good. So this is after doing that, let me go to full screen. So this is how my data now looks. Okay, so you see, this has been transformed, this has been transformed, this has been transformed, and that into numbers. Okay. So this is ordinal data. So we have dealt with ordinal data. Any question on our simple code on how to deal with ordinal data? I think it's as simple as it can get. Okay. So just a for loop through, have a list here saying what is ordinal, and then just transform it using an inbuilt function called label encoder from skitlearn or sklearn. Then the next thing, we are done with transforming that. We might want now to transform the nominal. Okay, so how do we transform the nominal? So here is where one hot actually comes in. And pandas has so one hot, we can also do it this way using an encoder, but pandas has a beautiful method for doing encoding. So one hot encoding. So I find it to be very, very easy. Okay, so the code looks like this. This is what is going to happen. So let me just take you through this. So we imported pandas as PD. So we're just going to say pd dot get dummies, okay? Because some dummy rows are going to be formed, but let's have a look at it so that we see how it's looking like. So get dummies is a function, okay? And then inside the function, you might want to transform, let's say, just one column. So let's say we transform location, where we have Karen and etc. So I just want to get dummies from location. Okay, so you just say data location, that returns the entire column for location. Okay, and then you want to set something called a prefix. You will see it when it shows up. You just want to say prefix, maybe estate or something. Okay, and then you see get dummies. You will actually see how it works. So let me see if that one is complete for us. So you see what it does. It one-hot encodes location, but it forms new columns for every estate that I had using my prefix. Okay, so I can say anything here. So in column 1, so if I may compare this one to my data, so this is one-hot encoding, but after one-hot encoding has been done, things are placed in their own columns. Why? Because if I place all these in one column, the training process will read this as 100, this one as 1, this one as 100, this one as 100, this one as 1,000, and we don't want that. So this is what one-hot encoding does. So you see here, column 1 had Karen. I don't know if you can zoom this one also. I want you to get this one. It will help you a lot. Good. So in the first row, now zooming has brought problems. Where is my estate? Okay, fine. So in the first row, I have Karen. So Karen is hot. So you see estate Karen is hot. 1 means hot, it's like binary. In the second one, I have Madaraka. So Madaraka is hot, everything else is cold. In the third one, I have Karen again. So you see Karen and Karen have the same. So this is one-hot encoding. And this is what one-hot encoding is going to do. But immediately, I know you should see a problem with one-hot encoding, which you are going to tell me after we are done. So this is one-hot encoding. Get dummies means that we are forming dummy rows, not rows, but columns, okay? And so we are going to throw away this, and then we are going to train on this. So we are going to form new rows. If I had 10 estates, I'm going to form 10 new rows, okay? So that's what get dummies does. I get dummy rows, which are one-hot encoded by default. So fine, so what do we want to do? Actually, we want to form a new data set with the dummy rows, and we want to throw away the other one. So what we just say is that the new data, so we say the new data is equal to, so we are going to form the dummies, then we are going to merge the dummies with the data set. So you can either merge 2 tables or 2 data frames using concatenate or join or merge, but now I'm just going to use concatenate. So I'm just going to say pd dot concat. That's the inbuilt method for concatenating. And here I can just concatenate 2 data frames like this. I can say data frame 1 and data frame 2 according to the documentation. And now what do we want to concatenate? That's the question. We want to get the original data set, okay, as it was, and we want to concatenate this guy. Yes, someone's mic is on. So I just bring the guy there. Good, then we can try and see the new data. But before you do that, instead of doing location only, because we want to do this for every nominal data, so I just did this, remove location, just type nominal. Let me see whose mic is on. Okay, fine. Okay, good. So fine, nominal here, and then the data. Then to tell the concatenator that you want to concatenate the columns and not the rows, you just normally say axis is equal to 1. Okay, you can check the documentation also on the same. Axis is equal to 1. Okay, fine. So mute everyone except me. Good. So I'll be done in a minute. You hang in there. So now, for all nominals, okay, I want to concatenate them. I want to throw away the other one. I've not written the code to throw away. The code to throw away, you can check how to delete rows here. And it's also how to delete columns. Okay, so we're just going to delete the other columns. We don't need them. So it's just the data, and then you say drop. So what are you going to drop? All the nominals. Okay. And I want to drop them according to the column and not the row. The row is the default, so I have to say. And then there's something here which you won't describe now. You just type true, like that. So this should transform our entire data set. Okay, that. So run that one. That one was okay. Then now run this one. So nominal is not defined. Okay, nominal. Okay, fine. Okay, so this is now our entire transformed data set. We've actually prepared this data. You can see we now have a much larger data set than the one we had. Any question up to there? I think it's straightforward and easy. Transforming nominal and also transforming ordinal. Okay, nominal and ordinal. So I just write the last piece of code, then I release you. The next thing now that we want to do, since we have the data, is now to do our feature selection, which is now the main part. So actually, how do you do feature selection? Number one, you have to do the following. So I'm just going to do this to define what is X. So X is capital because I have many X's. Okay, I have the estate, the location, the what and price. Not price, price is the target. So X is going to be data, and I'm just going to drop the last column. Okay, so the entire data minus price. Those are all my X's. Do this along the column. So axis 1, or you can just type that one. Y is going to be the data with just the price column. That's the target. So I have small y because y is only 1, but big X because there are other smaller x's inside X. Good. So there, it's actually X is equal to, not X. Okay, and Y is equal to. Can actually try and print. Let's see how X looks like. So you see X is everything minus the price. Okay, so price is the target. Let me print Y. Okay, you see it's only Y. So very quickly, because we are not writing the regressor ourselves, we are just going to say the regressor is just going to be lasso CV. Okay, so we just tell it, use the lasso from Skitlan. Then we're just going to say regressor dot fit. And then you're just going to give it X and Y, like that. Yes, so this dot fit means training is going to take place. So this will train, okay? So this will train, and training has just completed. Fine, so Lasso CV will optimize, and also at the same time, it will choose its own Lambda. Remember, Lambda has to be trained. No, it has to be set. So after the regressor has trained itself like this, it means that also in every iteration, okay, in every iteration, we were kind of setting the weights, okay, of all these x's, we were setting the weights. So now those weights that were set, they can actually be found inside now a variable. So the traditional regressor calls the weights the coefficients, okay, the coefficients, as we call them, the weights, okay. So it is actually going to be returned like this. We can access it like this, regressor dot coefficient. Okay, that will tell us all the weights. So we can actually quickly print it. It's going to be done here. What's regressor? Whatever you called it here. Okay, it becomes that. So these are all the weights. Okay, for all the features. You see already some weights are 0. These are the ones that are going to be dropped. Some weights are 0. So how do we deal with that? Very quickly, you have to finish these ones today. So now we can rewrite it into a data frame. Okay, so anytime we want to rewrite it into a data frame, we just say pd.series. That writes one column in a data frame. Series. Okay, so what's a series? It's just a column in a data frame. And then we are going to place this guy in here. Let me see what else I want to do. I just want to say the index is going to be defined by x dot columns, just a way to get all the columns in the x's from location to blah, 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 blah. Okay. And then I'm just going to store this. Can actually store it. Can say it's a new column or data phrase, data frame, okay, or anything. So you can just call it anything. I don't want to type anything because I like typing variables according to what they actually carry. So we can call it a coefficient row. No, column is equal to that, that entire thing. Okay, then actually, how do we view it now? Let me say, for example, print coefficient column. Okay, so that we see how it looks like. So comment this one out. So you see, the weight for this column has been set to this using the lasso. Lasso has reduced this to 0. So it means this is going to be dropped, that is going to be dropped, this one will remain. All the zeros are going to be dropped. You can see where your multicollinearity was. All of the guys are going to be dropped, but ambience is going to be maintained, okay? All these are going to be dropped. So yeah, so that is how feature selection happens. So some features are going to be dropped. This is the transformed data set. All the features with zeros are going to be dropped. The rest will remain. Any question up to that? No, it's just coding. So you can code and then start seeing. The next thing is just to visualize that one using matplotlib. And here we can actually just say we sort the values, and then maybe we plot them on a, can plot them on a pyplot. So then how do you sort the values? You can just take that one. You use the inbuilt function called sort values. So if I'm not wrong, sort values, yes. Okay, fine. And we can actually just store this into something, maybe sorted coefficients. Coef is equal to that. So this is the values that have been sorted. Okay, then we can just say sorted coef, and then we can just plot the guy. Dot plot. Good. I think that one should work for us. I don't know if I did the import up there. Yes, so you can actually see now there's a problem here. They are two clogged in together. Okay, so matplotlib, okay, dot how we normally set the size of a screen. Okay, don't cram this one, won't help much. The figure itself, and usually dot fig size. This is my last line, I promise. And then after that, I will go. Then I can just say what is the X value and the Y value. I'll say just 15 and maybe 11. I don't know. Let me see. Okay, fine. So now you can see Karen has this value and size is up there, and all these other features are set to 0. You can see actually there. This is too large. Okay, I have to zoom down now, or maybe just say this guy has a smaller size. Let's say 10, maybe 7. Hope that will not congest values. Okay, it's just a visualization thing. So even better, you can say, can specify the kind of plot that you want. You can just say kind here is equal to bar h. Okay, and then you can be able to see now what bar h actually does. Actually, now I'm at liberty to zoom. So conclusion, if I'm looking for an office and L1 has done feature selection, the most important features are the following: the ambience and the size, and whether the office is in Karen or not, proximity to the road and proximity to the mall. The rest are dropped, they don't matter. So when all is said and done, anyway, I have just a small data set, 10, not much. So this L1 will pick ambience, size, proximity to mall, proximity to road, and estate Karen in the transformed data set. Remember, we transformed to get all this. So these are the selected features. So out of I don't want to print anything else. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Out of 16 features, 1, 2, 3, 4, 5. 5 were chosen. Okay, and that's how we do feature selection using embedders. using Skitlearn. Any question? This, our very quick coding. The rest is just practice. You can do maybe better by doing more lines and checking out documentations and actually coding. But the most important thing here is one hot. You always need to have one hot. And how to transform nominal versus ordinal data. There are other encoding techniques that I will teach you. Good. So before I close it, I just want someone to tell me the disadvantage of one hot as an encoding feature. Let me see, data and data. We see what one hot was doing. So run that one, and then now run this one. So what do you think is the disadvantage of one hot encoding as a technique? Yes, Waweru, you have your hand up.
The dimensions become too many, especially if you have a, yeah.
Yes, very, 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 very good. Now, guys, if you're writing, yes, true. The dimensionality of the data increases by having the dummy rows, okay? So bottom line, one hot encoding will have dummy rows, okay? But the problem is that it increases dimensionality. That's a problem because if we want to do, actually we are trying to do feature selection to reduce the features, but Mr. One Hot is increasing the features. So it's like taking 10 steps forward and 19 steps back. Okay, so sometimes the balance is not that good. That's why from one hot encoding, we are going to have other types of encoding which don't increase dimensionality. What is dimensionality? Is just the number of rows. So very quickly, that's why I listed these ones here. Where is the task? We're finishing. And that's why I listed these ones here, okay? There's binary encoding, which is almost same as one hot, but there is a good encoding called backward difference encoding, which does not increase dimensionality, but actually maintains the information. Okay, so we'll check out these ones. Now you know how to prepare a basic data set before training. This is actually contradicting because we did feature selection after fitting the model, and that's because we are using the embedded technique and we are going to use these terms interchangeably. So that was a basic example on how you can prepare your data. So don't always feed unless you're doing decision trees. Anytime you see data like this, you have to transform it. And there are many other data that we can look at, and we will always be transforming the data set. So I hope you learned today. I will try now to prepare something small on maybe wrappers, which are also accurate in finding feature selection, and then give you a small assignment. For now, I think I can head over, eat a bit, and then now go to mark the labs. So if you have not uploaded, please do upload. I think today we can end up there. We can end it there unless there is a very pressing question. You can now relax. I will share the notebook as usual. You'll find it there on e-learning. All the best. So as you continue, let's meet on Friday. You can say hi to me there.